We are at the point in Chapter 5 now where we can use another lapse rate to predict the height and type of clouds. So again, we've had a number of lapse rates here. We've used environmental lapse rate to look at the stability of the atmosphere. We've looked at dry adiabatic lapse rate and dew point adiabatic lapse rate to detect the base of clouds. And we have looked at moist adiabatic lapse rate to look at the temperature inside clouds so that we can predict the type of precipitation that the clouds will be producing. Now we are going to look at the real messenger of the atmosphere, the type and the height of the clouds that you see going by in order to predict the weather. The two lapse rates that we use to determine the height of clouds in the near future will be the moist adiabatic lapse rate and the environmental lapse rate. So let's get into it for Chapter 5. And of course, it all starts with our observations. And we can observe that clouds have different heights. Some are rather tall, like this one, and some are quite short, like these clouds over Scotland would be a very short, a cloud without a lot of altitude to it. So we are going to learn how to predict this in the future based on the soundings that we see from the radiosondes. In those soundings, we will be looking at parcel lapse rates and environmental lapse rates. So we have already talked about the environmental lapse rates. Those are the red lines on the soundings. I need to introduce to you a little bit more about the parcel lapse rates and the difference between the two. Let's start with what you already know. The environmental lapse rate, the red line on the sounding, shows the actual temperature of the atmosphere at a particular altitude and pressure. And those are recorded twice a day all over the world. That actual temperature is impacted by everything in the atmosphere. It is impacted by the forcible lifts that we talked about. It's impacted by competing air masses that move into the area of the balloon. It's impacted by the expansional cooling of the atmosphere. It's impacted by the latent energy release of clouds when they condense water vapor or when they freeze water droplets. It is impacted by compressional warming of the atmosphere as well. So the balloon going up and recording records an environmental lapse rate that reflects everything going on in the atmosphere. On the other hand, the parcel lapse rate is an imaginary lapse rate of an imaginary sac of air that was collected at the ground, and we calculate the temperature of that imaginary sac from the ground up, so that we are doing our calculation based on the expansional cooling alone of the sac. We may put in the impact of force lift on the parcel lapse rate, but the vast majority of it is going to be the expansional cooling of the sac to condensation, and then the latent energy release at condensation or at freezing as we calculate that that sac of air should be condensing in the atmosphere and possibly rising as it condenses and freezes. In other words, this imaginary sac is not going to be calculating the impact of competing air masses because it's an imaginary sac. And it's not going to be calculating the result of compressional warming because we don't know where this sac is going to end up. So we are strictly going to be doing the calculations really based on the expansional cooling that we talked about. In other words, we're going to take the dry adiabatic lapse rate and move it up to the lifted condensation level. And then we're going to take the moist adiabatic lapse rate and figure in latent energy release with condensation and freezing. Strictly a calculation. Now, on the other hand, we can use the calculation, and we can use the calculation visually. Now, I recognize that this graphic here is a bit blown up, but it's a really important graphic, so I really wanted you to see it. And what it is showing to you is the environmental lapse rate, which would normally on a sounding be in red, and the actual temperature of the air. And it's showing you here the forced lift and the temperature loss over altitude that is associated probably with convection or maybe with convergent lift. And then it is showing to you the impact of the air temperature when the air is starting to stabilize. In other words, when the ground is emitting so much energy that the upper layers of the first set of the atmosphere is starting to warm, and it's not losing temperature as rapidly as it was before. So you might see this in the evening time, and then it will become a stable atmosphere, an isothermal atmosphere up here. In this case, where you have an environmental lapse rate like this, you're probably still going to get an average of a conditionally unstable atmosphere, but you see here that I've got a lot of stability in here until I get to the stratosphere. And that is the environmental lapse rate. Over here, right here, I am showing to you the model of a parcel with a moist adiabatic lapse rate. So in other words, the model says that the parcel follows the dry adiabatic lapse rate until the condensation level, and then follows the moist adiabatic lapse rate to predict the temperature of the cloud while it is condensing on vapor or while it is freezing water droplets. And if the temperature of the cloud is above the temperature of the environment, well, that cloud is going to be warm air rising up, and the cloud is going to continue to rise and grow. When we look at this visual representation of data, we can know this. I don't even need to know the exact temperature of the environment or the exact temperature of the cloud to know whether or not this cloud is going to rise up and grow and rise beyond its cumulus status. What I look for is the angle of these lapse rates. And when I see the angle of the moist adiabatic lapse rate for the parcel being a more straight line angle than the angle of the environmental lapse rate, then I know that this cloud is losing temperature at a more slow rate than the environment. I'm going to say that again. When I see that the moist adiabatic lapse rate has a very straight line stand up lapse rate, we might call it a steeper slope, but it's not really a slope, so that's why I'm not using those words. But when I see a steeper moist adiabatic lapse rate and compare that to a less steep environmental lapse rate, I know that the cloud parcel is losing temperature less rapidly and staying relatively warmer and staying relatively more buoyant. Now you may say to me, those look so identical, and I agree with you, they look very close. It takes really precise analysis of what you're seeing here. And what I would say is this: from the level of condensation up, I say that this lapse rate is steeper than just a bit than this lapse rate. It's not a big difference. And as soon as the cloud parcel gets to the isothermic section of the environmental lapse rate, it is now cooler than the environment, which is not losing any warmth at all in that isothermic area. So this is the top of the cloud. It can't ascend any faster. Let me give you another representation that might make it a little bit easier. In this particular slide, same thing. We are looking at moist adiabatic lapse rate and the steepness of the slope versus this this environmental lapse rate and the steepness of that slope. I think you can see that the moist adiabatic lapse rate is steeper. That means that the cloud is going to stay warmer than the environment. That means that the cloud will continue to rise. It will continue to rise to the point where it gets to an area where it is cooler than the environment. An isothermal environmental lapse rate is a perfect place to shut down and close off the lid of this cloud development. This is called a cumulus congestus cloud. It is the type of cloud that when you see it driving on 287, you say, ooh, that has so many nice shapes to it. That looks like such a neat cloud. Actually, that is a cloud which could potentially become a thunderstorm. A cumulus congestus has quite a bit of altitude to it and certainly has the energy to, in fact, power itself a little bit above the stable line here, the isothermic line, because it has quite a bit of energy to it and it can release enough latent energy at the top to kind of break through, which reminds me of clouds that tend to break through the stratosphere. A cumulonimbus cloud, and sorry that you can't see that as well as you need to, it says cumulonimbus down below there. Cumulonimbus cloud is the perfect candidate for a cloud with enough latent energy to break through the anvil in the stratosphere. But again, I think you can see here that the line for the moist adiabatic lapse rate is steeper than the line for the environmental lapse rate, meaning that this parcel is going to lose heat less quickly than the environment and is going to remain more buoyant to rise up until the point where the cloud is no longer warmer than the environment. You see in here, this is the stratosphere where the environmental lapse rate will start to increase because of the ozone absorption of sunlight. So we're trying to put everything together for you now to be able to predict the types of clouds and the altitudes of clouds. You've now looked at cumulo congestus and cumulonimbus clouds. On the next video, we're going to apply this to soundings like you see here and go over and put everything together so that you can start to read soundings and predict weather from the soundings. See you on the next video.